In this lecture, we're going to talk about backpropagation. Backpropagation is a technique or a set of techniques that can be used to compute the derivatives of certain quantities, for example, derivatives of the network parameters with respect to the loss function. And these derivatives are important to be used in conjunction with an optimization method that can then train the network. We will later in this lecture series learn about the standard algorithms such as stochastic gradient descent, RMS-prop, or ADAM. But for now, we'll rely on your general knowledge of machine learning, that you know how these optimization techniques are used to train machine learning algorithms. Also, this lecture might be a bit longer, so I might break it up into two parts. First, we're going to do some review of calculus, especially some multivariate calculus and the corresponding notation. Let's start in high school with a review of the derivative. So what we have is a function f of x that maps a scalar x in R into another scalar, let's say y, in R. So what we have here is a definition of a function that maps an input x, which is a scalar. Or let's look at this line here. There's this input x, which is a scalar, and as output we get this scalar y. And what the derivative in fact asks is, how does y change? How does y react to a very small, infinitely small change in x? So if we change x by a very tiny bit epsilon, either in the positive or negative direction, how is y affected? So, for example, if a small change in x creates a large change in y, then we can say that the function y is very sensitive to the input. Let's look at this definition. So, and notation, we have d f of x dx equals the limit of f of x plus h minus f of x divided by h. So we'll skip the figures because it's a bit too elementary. But what you can see here is that we have this f of x plus h, and this is sampling the function at a position that is x plus, and this is some tiny offset, and then we subtract the function at the current point x, so we subtract f of x. And then we divide by h, and we let h go towards 0. Now, this is an example. F of x equals 2x squared, and the derivative would be 4x. Again, the interpretation is, how does the output f of x or y change when adding a small value to the input x? Next, we will look at some of the notation that is used to describe derivatives, but my assumption here is that you know the derivative really, really well already. So here we see three notational systems: Leibniz notation, Lagrange notation, and Euler notation. So, for example, if y is a function of x, then you can see some notation dy dx, or you see some notation df dx. Now, sometimes you see notation that makes the input variable more explicit. So the f of x dx, or df and then the x written down here, dx, or d dx, this is more written like an operator, and then f of x written here like this. So all these types of notation are possible, and you can see them. Authors even mix them, and these type of notations are fairly common, fairly widespread. Then there's also sometimes this more explicit writing of a derivative at the point. So you could have the dy dx, and then there's a bar x equals a. That means that we have this derivative, but we want to evaluate at the point x equals a, so at the point a. Or dy dx evaluated at a, or d dx f of a. The Lagrange notation, which we will not use a lot in these slides, is f prime of x, or f prime prime of x for the next derivative. So something that you probably also have seen a lot. The Euler notation uses this d. So d is an operator mapping a function to another function, which is the derivative. So you would write d of f equals df dx. And so that d operates on this function f and gives you another function that is the derivative. In the following, I will use the Euler notation because I kind of like it. It's less to type in LaTeX to produce the slides. And from the Leibniz notation, just we use these partial derivatives. All right. And this type of notation with partial derivatives is what the Stanford lecture used, or now the Michigan lecture, that has been a lot of inspiration for these slides. So heavily featured in backpropagation is the chain rule. Let's review it for one variable. We have a function h of x that is decomposed of two functions. Let's look at the last part here. The function h of x is g of f of x. So x is the input, and first we apply f to the input x and get some intermediate result. And then to this intermediate result, we apply the function g. Another way to write this is to write that h is a function that is g ring f, and that is the subsequent execution of functions. So I also hope you've seen this notation. Now, also making that maybe more explicit with some naming of the intermediate variable. So we said that looking at g of f of x computes some intermediate output, and we could explicitly go and call this intermediate output u. So u equals f of x, and then in order to get the final result y, we have y equals g of u, where u is this intermediate output computed by f of x. The chain rule now tells us how can we compute the derivative of a function that is the composition of two, or then by repeated application, multiple nested functions. Okay, so we want to know the derivative of y, the final output, or the derivative of h of x dx, and we can decompose that as dy du dx. And so if you read this almost like regular fractions, then you could see, oh, okay, maybe we can, remove this, and then this kind of looks true from how we computed with fractions. And again, looking at the structure here, so we have dy du, which is kind of the derivative of this one here, and then du dx, this is the derivative here. So du dx asks, for this u equals f of x, how does this output u change with a small change in x? And dy du asks, for this function here, if u now changes a bit, how does the output y change? Also, in the Lagrange notation, h prime of x equals g prime f of x times f prime of x. So it's the derivative of the outer function times the derivative of the inner function. Somewhat, this notation seems to be a bit more explicit what is going on, and might be a bit easier to parse than what you see here. So that's why I have both of these versions. All right, now let's look at partial derivatives. Let's look at a somewhat simple function first, f of x, where x is a vector now, that takes an n-dimensional vector x and maps it on the real line. So we have an n-dimensional input and a one-dimensional output. So f of vector x can also be written as f of, and these are all the individual components, x1 to xn. The partial derivatives are then denoted as df dx1 to df dxn. And again, we have one single output. So what does this first element here tell us? It says, how does the output change with a small change in the variable x1, and so on and so forth until here. How does the output of the function change with a small change in xn? Again, we have all these input variables and one output, and then we would expect that the output depends a lot more on some of the variables, some of the input variables than others, and then for the variables where the output changes more, we would expect the partial derivatives to be larger, or at least larger in magnitude. So the example here is almost too simple, but we have f of two variables, x and y, so these are both scalars, and it's defined as x times y. So df dx equals y, and df dy equals x. So for this also, the expectation is that you know this really well from your undergrad studies, that is taught in almost any engineering and computer science undergrad degree fairly excessively. If not, you might want to look at some of these course notes and start catching up a bit. Next, we go to something that everybody should have learned, but now there is some distinction between what undergrad program you went to. Some of them now tend to be very light in mathematics, so we will also review that fairly slowly. We have now functions that have multiple inputs and multiple outputs. We have a function f that has n inputs and m outputs. And this is maybe a bit confusing. So why n and m here? So if we think of a matrix that computes a matrix vector, so a function that computes a matrix vector multiplication, then we will see that a function y equals ax has a matrix that is a matrix of size m times n. That one defines a function that has n inputs and m outputs. Now, but let's look at this derivative. So the derivative of this function f of x in this D notation is I mean, this is maybe not a very proper definition, but let's imagine it as a matrix of size m cross n, where we look at the sensitivity of each possible output to each possible input. So for each combination of input variable n and output variable, that means each of these n input variables and each of these m output variables, we could ask, how much does this ith output change with the jth input? So this is asked by this partial derivative, the fi, that is the ith output, dxj, this is the jth input. So if we have 100 inputs and 200 outputs, then we will have 100 times 200 partial derivative combinations. Now let's talk about some important thing about notation. There are different notational conventions, and these notational conventions make it really easy to get confused about derivatives. In fact, for myself, this has been the most difficult part of matrix and vector calculus, is whenever you look up something really quick on the internet, you look at some course notes, some slides, it is not that easy to figure out what is actually the notation here. And the two main ones are the numerator layout and the denominator layout. However, unfortunately, there are also mixed forms, and also mixed forms where the authors call them one of these two. And that leaves a lot of room for confusion. Now, let's look at these two and maybe make a few more comments. So, in the numerator layout, we have the following convention, that a derivative of a function Rn to R, these are functions that have many inputs but only one output, the derivative is a row vector. Even if we have the convention that vectors are column vectors. So the function would take a column vector as input, but the derivative of the function would actually be a row vector. Also in the numerator layout, the derivative of a function R that has one input and n outputs, this is now going to be a column vector. As we will see later, where we also review the gradient, the slightly confusing thing is that the gradient, which is also generally used as a synonym for the derivative in sloppy applied engineering mathematics, and the gradient is a column vector, and the derivative is a row vector. So what you see is that a bit later there will be many other choices how to orient something. but it's important to remember these two things are some of the main ones, and it is important also to remember that some of these layout conventions are mixed, and it's important to be careful, especially when then you go to matrices as input and output, or even higher order tensors. So this is an excellent slide I found from some lecture at Berkeley, where the numerator layout is reviewed, but it's also extended to inputs of that are tensors of higher rank. So again, as our short comment, a scalar we consider as rank 0 tensor, vector rank 1 tensor, matrix rank 2 tensor. And what we're looking at are functions that have inputs either scalar, vector, or matrix tensor of rank 2, and outputs either scalar, vector, or matrix tensor of rank 2. So what we can look at is how does the derivative look like if the input is a scalar and the output is a scalar. And that's the well-known high school case. Then dy dx is also a scalar. Now, what happens if the input is a vector? So the input is of size n times 1. Again, we have n inputs, and the output is a scalar. So this is the typical case that is handled in optimization lectures. We want to optimize a vector, a function that has a vector's input and a single scalar output. And so here, the derivative dy dx is this row vector, one row, and n columns. One other comment here is that you see that this notation here nicely extends to all of these cases by just writing partial, and then on top you can, these are the outputs, you can write a scalar, a vector, bold font, or a matrix tensor with capital letters, bold font. And down here, the same thing. So notationally, this is really nice to extend to all the different cases. Now here, you could say this shouldn't be a partial case, but this should be a dy dx. But actually, I like this consistency here a lot, and I guess also that's why they just write this same notation with the partial for all the cases. So now, let's again maybe look at this case. We have a vector as output, but only a single variable as input. So in this case, dy dx is a column vector. What happens, and this is a very common case that we also need to consider in this lecture, what happens if we have an input vector with n dimensions of a function and an output vector y with m dimensions. In this case, that's what we saw kind of here. The derivative dy dx is going to be a matrix, a rank 2 tensor with dimensions m and n. So there will be m times n values in this matrix. Well, now let's look at the cases that are very relevant to this class, but that we will not do because the notation might be too tricky. What happens if now the input or output are matrices? So let's, for example, say the input is a matrix X with dimensions n and k, and the output is a matrix Y with dimensions m and l. In this case, the derivative will be a rank 4 tensor with dimensions m, l, k, and n. That means we will have m times l times k times n values. This, in some sense, is not a problem. You can work with tensors, manipulate them, and there are tensor operations like manipulations. However, that's maybe a bit tricky, and the review of these tensor operations is a bit beyond the scope of this class. So, two remarks then. One is that, well, we not only have rank 2 tensors that we deal with, but we actually have a common case where the input to a computational node as well as the output are rank 3 tensors. These are going to be images with a certain depth. And then what happens if we have a rank 3 tensors input and a rank 3 tensors output? Extending this, we will get a rank 6 tensor as derivative, and the order of the dimensions follows this pattern. So then it gets even more complicated, but to make it less complicated, we could think of a function that has a matrix or tensors input. In our mind, conceptually, at least we could unroll these inputs and outputs into vectors, and therefore notationally reduce it to this case here, where input and output are vectors, and we'll have a derivative matrix of signs m and n. So, for example, we are in this case, let's say, where we have matrix input, matrix output. We could also move it to this case here, the vector case, where we would say, okay, out of this matrix with n times k elements, we simply make a vector with m times k elements, and out of this matrix with m times l elements, we make a vector with m times l elements. So this helps us to reduce the matrix case to the vector case. As you will see in the following, there are some practical considerations for this whole notational system. When we're going to work with backpropagation, we're going to use a lot of visual aids using graph drawing. And there it is convenient if the derivatives are drawn traveling on graph edges. That will be very intuitive. And what we would like is that these derivatives traveling on graph edges, this could be any type of tensor, scalars, vector matrices, will have the same shape as the data traveling on the edges. So generally how we drew these graphs before, the data was traveling on edges, generally from left to right in our drawings. I mean, they were from the inputs to the outputs. And what we will see is that when we study backpropagation, the derivatives will travel starting from the final output of the network backwards. That also explains this term backpropagation, will travel backwards. And then every edge in the forward direction will have the data traveling on that edge. And then in the backward direction, there will be the derivative traveling in the opposite direction. Also for the implementation, the derivatives should be stored in the same data structure type as the data. So you would like to probably have some implementation where you don't want to deal with all these transposes. Of course, this is some sort of a design choice. It's just that for the figures that I have in this lecture, we will see that this is true. The derivatives, they will not be shown in some sort of a transposed fashion. They will just be of the same size, and we will make the dimensions match up in such a way so that if there's a vector traveling and this is a column vector, then the derivative or the gradient of that will be shown basically using the same dimensions. Okay, so let's look at a few examples that are important and are for networks, and we'll look at them with the numerator layout. So let's say we have a linear layer, and the linear layer has a weight matrix A that has m rows and n columns. That means it will map n inputs to m outputs. And so this linear layer computes a function f of a vector x. Again, x has n components, and the output f of x is computed as a times x, where x is maybe some vectorized image that comes into this linear layer, this fully connected layer, and a are the weights of the network. And we'll use a here because a, this is the typical derivative you see if you look up matrix calculus on the internet, and this is written with a and x. Alternatively, we could also write it as y, the output y equals a times x. So this first line and the second line is just different notation for the same thing. Then the derivative of this function of this linear layer is a. That means the derivative with respect to x. So dy, the output, with the derivative with respect to the vector x. So this means that this matrix A itself, since it's also the derivative, can be interpreted. If you look at one element in the ith row and the jth column, it tells you how much does output I depend on the input j. So actually studying this derivative takes some time, and it really helps doing this visually, writing it down with an example, and really convincing yourself that this is true. That if you look at some element in the matrix, let's say the element 2, 3, that this really tells you something about the second output and how it depends on the third input. An example lecture that goes a bit more detail about this matrix vector multiplication and some illustrations is Stephen Boyd's lecture on linear dynamical systems that's available online in lecture form, and it also has the slides online. Let's go to the next example. F of x equals the squared 2 norm of the vector x. Then the f of x equals 2 times x transpose. So let's go one more. A ReLU, a condition evaluates to 1 if true. So we say that x1 greater equals to 0. This is like a conditional statement, and if it's true, it evaluates to 1, and if it's not true, it evaluates to 0. Now, if you have f of x, that is a vector valued x as input, so we have, if x has dimension n, then the output also has dimension n, and it's component-wise ReLU of x. So that means the derivative of x is a diagonal matrix that has kind of zeros everywhere except on the diagonal, and the diagonal elements are either 1 if the corresponding element in x is greater equal to 0, that is positive, or 0. Alright, I just noticed there is some formatting error, so this y, this should be a vector, of course, so this should be bold, and this also should be bold. But if we look at this, then we'll see, again, the general problem, we have a function that has an input x, and the x is a vector that has n dimensions, but here the derivative, because we have m outputs and n inputs, the derivative is a matrix, so the derivative with respect to x is a lot bigger in terms of, has a lot more individual components than the input x. And this kind of data explosion problem is something that this backpropagation algorithm helps us to bring under control somehow, so that we don't have to deal with these potentially very large matrices. All right, we learned about normalization, for example, batch normalization. And we need to make sure that we can actually backpropagate through normalization layers, that we are actually able to compute the derivatives of something like mean and variance. So the mean mu of x, or f of x, is a function that has n inputs and only one single output. So the function is computed by 1 divided by n, and n is the number of components in x. So summing up all the components. And so the derivative then is simply 1 divided by n, 1 divided by n, 1 divided by n, and however long the input vector x is. So the derivative is this row vector, and each element of this row vector is 1 divided by n. So this can be simply verified if we look at this expression and we look at the partial derivative of the output with respect to one particular input xi, so let's say x7, then all the elements in the sum that don't contain x7 would be 0 by the derivative rule, and the one element of the sum that contains x7, the derivative here, this would be 1, and then we have this constant 1 divided by n. So for all xi, this partial derivative will evaluate to 1 divided by n. Okay, a bit more difficult. Let's look at the variance next. So the function, this would be f of x equals 1 divided by n. xi, so the sum over all the components in the vector, xi minus the mean of x, and that is squared. So the difficulty here seems to be that mu, the mean, is also a function of x, and therefore this cannot be simply ignored when computing the derivative. Alright, so the derivative of f of x is, okay, so derivative is 2 divided by n x transpose minus mu 1 transpose. And 1 is a vector that has all ones and is n, has n components, has n elements. Let's just make a shape check. This looks like a row vector, that's good, and the row vector has n components, so that also looks good. We have a function here that has n inputs and 1 output, so that at least seems to be a tensor, a vector of the right shape. Okay, let's derive this. So we have the expression of the variance, it's copied from above, 1 divided, except for this mu, we just don't write mu of x to save us some time, but this is important to remember that this depends on x. And we want to compute the partial derivative d dxi, So we'll write this for every xi, and then we'll kind of go back and just knowing what it is for every xi, we can write the complete equation for the complete vector. All right, so we'll just look at one component of the derivative here. All right, so we have this. We'll apply the chain rule. We'll have the derivative of this times the inner derivative. So what is the derivative of something squared? Is 2 times whatever's inside the bracket. And then the inner derivative is going to be whatever the derivative is by the chain rule. So we'll need to expand this inner derivative next. So looking at this is the partial derivative of sum, so we can look at both of these elements separately. So this mu dx, we know that this is 1 divided by n. So we'll have this big sum, and so we look at this partial derivative for all, we sum over j for all xj minus mu derived with respect to xi, and for all these possible elements, mu dxi will always be 1 divided by n. And since there's a minus here, there will be a term minus 1 divided by n for all elements that we catch here in the sum. And so you will see there's this term minus 1 divided by n that will be put forward and multiplied. So out of this 1 divided by n times minus 1 divided by n, we obtain this new factor minus 1 divided by n squared. And this comes from deriving mu partial xi. Now this here, the xj partial xi, this will be always 0 except for when we have partial xi. In this case, this will be 1. So when this hits, there will be one single case. So we have this, there's no more sum. There will be a single time when this will be 1. So we'll have a single time where we multiply, where we get this, and this is the case when xj is xi. So we'll get 1 more, 1 divided by n, 2 xi minus mu. And that's what's written here. And then we sum together, and so we get this solution. And then we have to write it in vector form. So we'll do this, and we'll obtain this is the final solution. Okay, just some other small exercise for shape. So we have a function that has 3 inputs, x1, x2, x3, and 2 outputs. The first output is x1 minus x2 squared, and the second output is x1 times x3. Then the derivative is a matrix that has, again, as many columns as we have inputs and as many rows as we have outputs. So, for example, this element 1 here is how does the first output depend on the first input. Okay, so this is partial x1 of this expression here. So this is 1. This is how does the first output depend on the second input. Okay, this is this. So 2 minus 2 times x2, this is correct. And how does the first output depend on the third input x3? It doesn't depend on it at all, so we have a 0 here. All right. So the chain rule written down with multiple dimensions, again, we'll have 2 ways, 2 types of notation. We have 2 functions. One function has m inputs and k outputs, and the other one has n inputs and m outputs. So first, we need to apply this function because overall the function has n inputs and k outputs. So first we apply f to go from n to m dimensions, and then we go from m dimensions to k dimensions here. And we could evaluate this at a particular point a. All right, so we say the derivative of G ring F at point A is the derivative of G evaluated at f of A subsequent execution of derivative of f at the point A. Also, just for completeness, I kind of found this and liked it. So we have this Jacobian notation. The Jacobian G ring F is the Jacobian of G evaluated at f of A and times the Jacobian of f of A. And the Jacobian is basically the derivative in the case where we have a function with multiple inputs and multiple outputs. Now, again, as we do this sloppy engineering applied mathematics, but don't give any proper definition, we'll just think of the Jacobian as a matrix that collects all these partial derivatives. Okay, here we review one more term, the gradient. And in this case, we have a function with multiple inputs and one output. And again, the gradient is then very popular in optimization, the optimization literature, because there we're treating these functions that have typically one output. And the gradient is also a vector that collects the partial derivatives. So the notation is this gradient symbol f of x. And an example, okay, we have like f of xy equals xy, and then the gradient of f is y and x. So the gradient is almost the same as the derivative in numerator layout, except that the gradient of the function is the derivative transpose. So again, the derivative is a row vector and the gradient is a column vector. However, since this is also similar, and since we're kind of doing these practical applied computations, a gradient and derivative are generally used interchangeable. So you'll see lectures and different people just referring to backpropagation, you know, computing gradients or computing derivatives, and they use these terms interchangeably. So for interpretation, let's say you stand on some n-dimensional mountain, maybe just a regular mountain, and then the gradient points into the direction of steepest ascent. You want to go to the nearest peak. In which direction should I go to? Where do you go up the most locally? Or let's say you are at a point in an n-dimensional room, let's say a 3-dimensional room, the temperature gradient points in the direction of maximum temperature increase. So where locally you have the biggest increase in temperature. So let's look at this visualization for optimization typically. Let's say we are at some starting point on this terrain. We are here. And this terrain red is high and blue is low. And in optimization, you can say I either want to maximize or minimize. A lot of the literature now says, okay, we want to minimize. Also this lecture, we will want to minimize the loss function. So we are here, and the gradient tells us where can I go up the most. And the inverse direction, the negative gradient direction, tells me where can I go down the most. And so for minimization of a loss function, that's what I want to do. So then if I'm at some particular point here, and you can imagine that this now is a neural network that has only two parameters, theta 0, theta 1, Of course, in real life, we'll have millions of parameters, but the visualization in 2D holds. So we have some starting point here. And then you'll ask the network at my particular starting point, what is the gradient with respect to the network weights of the loss function? And then it's going to give you a direction that goes down locally the steepest. So, and then you go some tiny step in that direction. So maybe go down here, so then we're here. And then again, you'll start. So this is gonna process in mini batches. So you get some other, let's say, mini batch of images. Maybe you get 64 images. You compute the gradient of the neural network with respect to these 64 images. And then the gradient, you go the negative direction to make another small step. And then hopefully after many iterations, many mini batches, you'll eventually end up at some point that is pretty low, that is a good, we cannot even say it converges to a local minimum, but hopefully at some point that's close to some local minimum. All right, so this is basically the calculus review, and okay, I took quite some time for it, but what we use this for is then what we want to do next, which is automatic differentiation. And so here we will then look at this automatic differentiation, how this is done in neural networks. Okay, I'm going to take a break here and then resume recording the rest as a new video. Thanks.